On February 4th, 2026, at 0741 Universal Time, the sun cracked open and released an X8.1 flare. Most people saw the headlines, checked for aurora forecasts, then moved on when they heard the coronal mass ejection missed Earth. Relief. Safety. Except here's what they didn't tell you. The flare wasn't the event. It was the warning shot. Active Region 4366 has rotated out of view, but something larger just exploded on the far side, and it's turning to face us now. The question isn't whether a G4 storm is coming. The question is whether we're ready for what happens when multiple magnetic systems decide to act in concert. Stay with me, because what's unfolding isn't in the textbooks. Subscribe and follow along, because the solar drama unfolding this February is just the opening act, and the stage is set for more. Additional active regions are emerging. They're rotating into view even now, carrying magnetic flux from the solar interior, shaped by processes we observe but don't fully control. We can't determine which will fragment harmlessly and which will produce the next major event. But if the sequence from AR 4366 demonstrated anything, it's that predictability breaks down precisely when we need it most, when the sun transitions between stable and chaotic states. The flare erupted at 0741 Universal Time on February 4th, 2026. Active Region 4366, a sunspot complex that had been churning with magnetic fury for days, finally cracked open and released what scientists classify as an X8.1 solar flare. To put that in perspective, X-class flares are the strongest category we have, and anything above X10 enters territory we've only seen a handful of times in modern observation history. An X8.1 is not quite apocalyptic, but it's close enough to make every space weather forecaster sit up straight and reach for their coffee. Here's what you need to understand right now. The X8.1 flare that erupted from active region 4366 was not the event. It was the signal. Think of it as the crack of thunder that makes you look up and realize the storm is already overhead. Most people heard about it, saw the headlines, maybe even checked to see if they'd get to witness aurora from their backyard, and then went back to their lives when the alert said the coronal mass ejection missed Earth. They assumed they'd dodged a bullet. They assumed wrong. Let me explain why that assumption is dangerous. A solar flare and a coronal mass ejection are not the same thing, even though they often occur together. A flare is a flash of electromagnetic radiation, light, and X-rays that travel at the speed of light and arrive at Earth in about 8 minutes. It's energy, pure and simple. A CME, on the other hand, is a physical eruption of magnetized plasma, billions of tons of solar material hurled into space like a cannonball fired from the surface of the sun. CMEs travel much slower, taking anywhere from 15 hours to several days to reach Earth depending on their speed. The X8.1 flare hit us instantly with a burst of radiation that briefly disrupted radio communications on the sunlit side of Earth. But the CME, the part that could have triggered a major geomagnetic storm, was aimed slightly off target and glanced past our planet's magnetic field. Most people heard "missed Earth" and moved on. But here's the part nobody's talking about. Just because the mass ejection missed doesn't mean the danger has passed. The electromagnetic pulse from the flare itself was significant enough to cause a brief but measurable disturbance in Earth's ionosphere, that electrically charged layer of atmosphere between about 60 and 600 kilometers altitude. Radio operators on the day side of Earth, the hemisphere facing the sun when the flare erupted, experienced what's called a shortwave fade-out. High-frequency radio signals that normally bounce off the ionosphere to enable long-distance communication were absorbed instead, creating dead zones that lasted nearly an hour. Aviation frequencies crackled with static. Ham radio enthusiasts logged the disruption in their journals. Emergency services that still rely on HF backup systems had to switch to alternate channels. It wasn't catastrophic, but it was noticeable, and it served as a reminder that even when a CME misses, the flare itself carries consequences. Active Region 4366 didn't just produce one X-class flare. It produced 6 of them in roughly 10 days. 6! To give you a sense of scale, the average solar cycle sees maybe 50 to 100 X-class flares total, spread across 11 years. 6 in 10 days is not normal, even near solar maximum when the sun is at its most violent. Statistically, it's uncomfortable. It's the kind of clustering that makes solar physicists start using words like anomalous and elevated risk in their papers, even if they won't say it that way in press releases. Why does clustering matter more than individual flare strength? Because it tells us something about the underlying magnetic structure. A single powerful flare can be a one-off, a brief moment of instability that releases and then settles. But repeated flares, especially at this intensity, suggest the magnetic field isn't just unstable. It's fractured. It's breaking apart from the inside, while still generating extreme energy. Imagine a bridge with cracks spreading through its supports, but instead of collapsing, the traffic load keeps increasing. The structure is compromised, but the stress hasn't been fully released. That's Active Region 4366. Each successive flare in the series revealed something about the progression of magnetic decay, except that what we witnessed wasn't exactly decay in the conventional sense. The first X-class flare, an X2.3 on April 25th, appeared to be a standard eruption from a mature sunspot group with well-developed penumbral structure. The second, an X3.7 2 days later, came from a slightly different location within the same region, suggesting the magnetic stress had migrated. By the time the X8.1 erupted on May 4th, the Sunspot complex had fired off 2 more X-class events and exhibited signs of structural reorganization that puzzled observers. The energy wasn't simply bleeding off into space. It was moving, reconfiguring, finding new pathways to the surface. And here's where it gets stranger. As AR4366 was firing off these X-class flares, observers noticed something unusual. The Sunspot Group itself was physically fragmenting. Sunspots are regions where intense magnetic fields push up through the sun's surface, suppressing convection and creating cooler, darker patches. When a sunspot group starts to break apart, we'd normally expect the magnetic energy to dissipate, to spread out and weaken. But AR4366 wasn't weakening. It was shattering into pieces while maintaining, or even intensifying, its magnetic output. That's not supposed to happen. The fragmentation pattern was particularly strange. Instead of a gradual dissolution from the edges inward, which is typical for decaying sunspot groups, AR4366 seemed to crack along internal fault lines, creating smaller but intensely magnetic islands separated by rapidly evolving neutral zones. Solar magnetograms, which map the strength and polarity of magnetic fields on the sun's surface, showed that these fragments retained their delta-class characteristics. That's the configuration where opposite magnetic polarities are jammed together in close proximity, creating extreme magnetic gradients and tremendous stored energy. It's the solar equivalent of forcing the positive and negative terminals of a battery to touch without allowing them to neutralize. The tension builds until something has to give. NOAA's Space Weather Prediction Center issued forecasts that ranged from moderate to strong geomagnetic storm potential, peaking around G3 on their 5-point scale. Those forecasts were conservative, appropriately so. They're based on models that track known coronal mass ejections, calculate their speed and trajectory, and predict how they'll interact with Earth's magnetosphere. But here's the tension. Those models are excellent at predicting what we can see. They're less equipped to handle what's brewing beneath the surface, the magnetic complexity that hasn't erupted yet, but is building towards something we can't measure until it happens. Conservative forecasting doesn't equal absence of risk. It means we're watching the visible pieces and hoping the invisible ones don't surprise us. The forecasting models rely heavily on coronagraph imagery from satellites like SOHO and Stereo, instruments that can detect the mass and speed of CMEs as they erupt into the corona and propagate through interplanetary space. When a CME is launched directly toward Earth, these models can calculate arrival time within a few hours and estimate the magnetic field strength and orientation with reasonable accuracy. But they can't predict what hasn't erupted yet. They can't see the magnetic flux ropes coiling beneath the photosphere, the twisted field lines winding tighter in the sun's convective zone, the next eruption waiting for the right trigger. The forecasts tell us what's already in motion. They're silent about what's still loading. The sun is a ball of plasma held together by gravity and twisted into knots by its own rotation and magnetic fields. It doesn't follow a script. It doesn't calm down just because a flare has erupted and a CME has been launched. Sometimes the energy doesn't leave. Sometimes it redistributes. Sometimes the danger doesn't go away. It just changes form and waits for the next opportunity. Active regions 4366 gave us an X8.1 flare and 5 others before it. And then it did something that should concern anyone paying attention. It rotated out of view, off the edge of the sun's visible disk from our perspective here on Earth, and disappeared from direct observation. Most people think that means the threat is over. They think when a sunspot rotates away from facing Earth, we're safe. But the sun doesn't stop when we stop watching. The rotation happened gradually over the course of May 5th and 6th, as the sun's differential rotation carried AR 4366 westward across the solar disk from our perspective. By May 7th, the region had crossed the limb, that curved edge where the sun's surface disappears from view, and entered the far side where our direct observation capabilities end. Space weather bulletins noted the region's departure with the kind of relieved tone you'd use when a difficult houseguest finally leaves. The immediate Earth-facing threat was gone. But that's where the real uncertainty began. Because unlike a houseguest who drives away and disappears into the distance, AR 4366 didn't leave the neighborhood. It just walked around to the other side of the house, and we lost the ability to see what it was doing. There's a psychological trap we all fall into when it comes to space weather. It's simple, understandable, and completely wrong. The trap is this: if a dangerous sunspot isn't facing Earth, we're safe, out of sight, out of danger. It makes intuitive sense. After all, a CME launched from the far side of the sun would have to travel in the opposite direction from Earth. We're shielded by 93 million miles of empty space and the sun's own bulk. Except that logic only works if you're thinking about immediate threat, and it completely ignores what happens when that sunspot comes back around. The comfort we feel when a threatening active region rotates away is built on a foundation of spatial thinking that doesn't account for temporal dynamics. Yes, a far-side CME can't hit us directly. The geometry doesn't allow it. But that's like saying you're safe from a hurricane, because it's currently on the other side of the state. True for the moment, perhaps, but hurricanes move, and so do sunspots. The question isn't whether you're safe right now. The question is, what's happening to that system while you can't see it, and what state it will be in when it comes back into view. The sun rotates roughly once every 27 days, as seen from Earth, a bit faster at the equator, a bit slower at the poles. When a sunspot group like active region 4366 rotates off the visible disk, it spends about 14 days on the far side, hidden from view, before it can rotate back into Earth-facing position. During those 14 days, we can't see it directly. Our satellites, our telescopes, all of our optical instruments are useless because we're staring at a star and the thing we want to observe is on the other side of that star. But that doesn't mean we're blind. Scientists have developed methods to detect activity on the sun's far side, and they're surprisingly effective. One technique is helioseismology, which is exactly what it sounds like. Listening to the sun's vibrations. The sun rings like a bell, constantly oscillating with acoustic waves generated by convection and turbulence in its outer layers. When a sunspot or active region exists on the far side, it changes the local wave speed, and those changes ripple through the sun's interior. By measuring how those waves arrive at the near side, scientists can infer the presence and approximate size of far-side active regions. It's not as precise as direct imaging, but it works. The physics behind helioseismology is elegant in its simplicity. Acoustic waves, essentially sound waves traveling through the sun's plasma, move at speeds determined by local temperature, pressure, and density. Sunspot, with its strong magnetic field and suppressed convection, creates a region where these parameters differ from the surrounding photosphere. When waves pass through or reflect off these magnetic structures, their travel times change by tiny amounts, milliseconds or less. But those tiny timing differences, measured across thousands of wave paths crisscrossing the solar interior, can be inverted mathematically to create a rough map of far-side activity. It's like using echoes in a cave to map the chamber's shape without ever seeing it directly. Another method relies on the fact that powerful solar flares emit radiation in all directions, including light that doesn't travel directly toward Earth, but instead reflects or scatters off the solar corona, an interplanetary medium. When a major flare occurs on the far side, we can sometimes detect the indirect signature, a flash of X-rays or extreme ultraviolet light bouncing back toward our instruments. It's faint, it's tricky to interpret, but it tells us something big just happened over there, out of our line of sight. The extreme ultraviolet imagers on satellites like SDO, the Solar Dynamics Observatory, are sensitive enough to pick up these scattered signals. The coronal plasma above the far side flare site gets superheated to millions of degrees and emits strongly in EUV wavelengths. Some of that light scatters off the extended corona that we can see from our vantage point, creating a diffuse brightening that experienced analysts can recognize as the signature of a hidden eruption. It's not a direct observation, more like seeing the flash of lightning reflected in clouds and inferring there's a storm beyond the horizon. But when you see that flash, you know something powerful just released. And here's where the timeline gets uncomfortable. As active region 4366 rotated away from Earth-facing position in early May 2026, observers detected a major energetic event on the sun's far side. The timing was almost simultaneous. A R4366 disappears from view, and suddenly there's an explosion on the other side of the sun. Now, you might think that's just coincidence. The sun is a big place. Active regions come and go, and solar maximum is a chaotic time. Lots of things are happening at once, but timing, in this case, matters more than location. The far side event was detected on May 8th, less than 24 hours after AR4366 crossed the western limb. Helioseismic data showed a strong magnetic signature at approximately the same latitude where AR4366 had been located, just rotated 180 degrees around to the far hemisphere. EUV scatter signals indicated a significant energetic release, possibly X-class level, though without direct observation, the exact magnitude remained uncertain. The coincidence of timing and location was striking enough that several solar physics groups issued informal notes to colleagues, flagging the event as potentially related to the active region that had just rotated out of view. Not proof, but enough to raise eyebrows. If you go back through the historical records of major geomagnetic storms, the G3 and G4 events that knocked out power grids or fried satellites, you'll notice a pattern. Many of them were preceded by exactly this kind of handoff. An active region produces flares, rotates out of view, and then something significant happens on the far side. 2 weeks later, when the rotation brings that region, or something connected to it, back into Earth-facing position, all hell breaks loose. It's happened before. It could be happening again. The Halloween storms of October 2003 are a textbook example. Active region 486, later renumbered as 486 in the revised numbering system, produced a series of major flares in late October as it crossed the solar disk. As it rotated away, far-side activity was detected. When it returned in early November, it had reorganized into an even more complex and dangerous configuration, ultimately producing the famous X-28 flare, one of the most powerful ever recorded. The 2-week far-side interval wasn't a cooling-off period. It was an evolution period, a time when the magnetic structure continued to develop out of sight, emerging stronger and more volatile than before. This raises a central mystery that scientists are still grappling with. When we detect activity on the far side, are we looking at a completely new active region that just emerged in a different location? Or are we seeing the same magnetic system, the same structure, expressing itself in a new way? The sun's magnetic field isn't a collection of isolated patches. It's a continuous, interconnected network of field lines that weave through the solar interior and erupt at the surface wherever the conditions are right. Imagine a vast submerged root system, and what we call individual sunspots are just the visible branches poking up through the ground. If that's the case, then active region 4366 might not be gone at all. It might just be changing masks. The concept of magnetic connectivity beneath the photosphere is supported by observations of active region emergence patterns and decay timescales. Magnetic flux doesn't just appear at the surface randomly. It rises from deep in the convection zone, where the solar dynamo generates field through the interaction of rotation and turbulent plasma flows. These flux tubes, coherent bundles of magnetic field lines, can be enormous, extending across significant fractions of the solar radius. When such a tube breaches the surface, it doesn't necessarily emerge all at once. Instead, portions of it can rise at different times and locations, creating what appears to be separate active regions, but are actually different expressions of the same underlying structure. If AR 4366 and the far side, activity detected on May 8th are connected through a subsurface magnetic system, then the energy that powered those 6 X-class flares hasn't been exhausted. It's been redistributed. The visible sunspot, fragmenting, and the simultaneous far-side eruption could represent a magnetic restructuring, where flux is submerging in one location and re-emerging in another, maintaining or even amplifying the total energy budget of the system. This isn't speculation without precedent. Solar physicists have documented cases where active regions appear to dive beneath the surface and reappear days or weeks later, sometimes at slightly different longitudes with renewed vigor. The question isn't whether something dangerous is happening on the far side. We know it is. The question is whether that danger is independent of AR 4366, or whether we're watching the same engine rev up for a second act. Because if it's the latter, if the magnetic energy that powered those 6 X-class flares is still intact, still building, still connected beneath the surface, then the rotation back into Earth-facing position in mid to late May isn't just a calendar event. It's a countdown. And we don't know what we're counting down to. The mathematics of solar rotation give us a precise window for when that far-side activity will rotate back into view. Assuming the event occurred at roughly the same latitude as AR 4366, around 15 degrees north of the solar equator, the rotation period at that latitude is approximately 26.5 days. With the far-side event detected on May 8th, the return to Earth-facing central meridian, The imaginary line down the middle of the sun's visible disk from our perspective would occur around May 22nd. Give or take a day for uncertainties in exact position and differential rotation effects. That's the window. That's when we'll know whether the far side has been gestating something new or whether AR-436-6 has merely been gathering strength in the dark. Let me tell you what's supposed to happen to a sunspot group after it blows its load with multiple X-class flares. It's supposed to calm down. The magnetic field lines that were twisted and sheared and compressed to the breaking point are supposed to relax, to spread out, to lose their tension. The sunspot itself, that dark blotch on the sun's surface, is supposed to fragment and fade as the magnetic pressure drops and convection starts to reassert itself. Within days, maybe a week, the active region should decay into scattered remnants and eventually disappear entirely. That's the normal life cycle. That's what the textbooks say. The physics of sunspot decay is well established, or at least we thought it was. When magnetic flux emerges at the solar surface, it fights against the natural convective motions that want to mix and homogenize the plasma. The magnetic field is like a dam holding back a river. It can maintain that barrier. For a while, suppressing convection and creating the cooler, darker region we call a sunspot. But dams don't last forever, especially when the pressure behind them is constantly fluctuating. Eventually, the magnetic field weakens through a combination of processes. Flux cancellation, where opposite polarities meet and annihilate. Fragmentation as the coherent structure breaks into smaller pieces, and simple erosion as the convective flows gradually chip away at the edges. The timeline varies depending on the size and strength of the initial emergence, but for a major active region that's just produced multiple X-class flares, we'd expect significant decay within 3 to 5 days. The energy has been released. The system should be winding down. Active region 436-6 didn't read the textbooks. After unleashing 6 X-class flares in 10 days, it should have been a spent force. Instead, it fragmented physically while maintaining its magnetic strength. The Sunspot Group broke into smaller pieces, scattered across a wider area, but the underlying magnetic field remained intense. Observers noted that the Delta-class magnetic configuration, the most dangerous type where opposite magnetic polarities are crammed together in close proximity, persisted even as the visible structure fell apart. It's like watching a skyscraper crack and tilt, but somehow still holding all its weight. The architecture is compromised, but the load-bearing capacity hasn't collapsed. That's not normal. Magnetogram sequences from the Solar Dynamics Observatory showed the fragmentation in stark detail. On May 1st, before the X8.1 flare, AR-4366 appeared as a relatively compact group with a well-defined central delta structure surrounded by more diffuse plage, the bright chromospheric emission that typically accompanies active regions. By May 5th, after the final X-class eruption, the visual structure had changed dramatically. The once coherent sunspot had split into at least 4 distinct fragments, each separated by rapidly evolving neutral lines where the magnetic polarity flipped from positive to negative. But when you looked at the magnetic field strength rather than just the visual appearance, the numbers hadn't dropped nearly as much as they should have. Total magnetic flux through the fragments remained above 80% of the pre-flare maximum. The field was rearranging, not dissipating. Delta-class magnetic configurations are rare and dangerous because they're fundamentally unstable. Magnetic field lines want to align in smooth, orderly patterns, but in a delta configuration, they're forced into sharp, convoluted shapes that store enormous amounts of energy. When that energy releases, you get flares and CMEs. The fact that AR-4366 maintained a delta core even after fragmenting suggests the energy didn't fully release. It's still there, coiled up, waiting. To understand why delta configurations are so volatile, you need to think about magnetic topology. In a simple bipolar sunspot group, which is the most common type, you have a leading spot of one polarity and a trailing spot of the opposite polarity, connected by smoothly arching magnetic field lines that rise from one spot and descend into the other. This configuration is relatively stable because the field lines aren't fighting each other. They flow naturally from source to sink. But in a delta configuration, you have opposite polarities jammed into the same umbral structure, sometimes within a single penumbra. The field lines can't form smooth arches because they're forced into tight, highly sheared geometries. It's like trying to tie a rope into a knot that physics doesn't want to support. The tension builds until the field lines either reconnect violently, releasing the stored energy as a flare, or the whole structure comes apart. What makes AR4366's behavior so puzzling is that it did both. It released enormous amounts of energy through those 6 X-class flares, suggesting violent magnetic reconnection was occurring, but it also fragmented structurally, which should have resolved the delta configuration by separating the conflicting polarities. Instead, the delta characteristics persisted in the fragments, as if the underlying magnetic field was continuously regenerating the unstable geometry even as the surface structure tried to fall apart. That implies a sustained energy source, something driving the system from below rather than simply unwinding existing stress. Now here's where we enter hypothesis territory, and I want to be clear about that. What I'm about to describe is not confirmed fact. It's a scenario that some solar physicists discuss quietly in the corridors of conferences, but rarely in published papers because it's speculative and uncomfortable. The hypothesis is this: magnetic energy from an active region can submerge. Instead of erupting outward into space or dissipating into the surrounding corona, it can sink back down beneath the photosphere, the sun's visible surface, and continue to evolve out of sight. Think of it like a tensioned spring pushed underwater. You can't see it anymore, but it's still compressed. It's still storing energy. And if it rises back to the surface later, it doesn't emerge relaxed and harmless. It emerges coiled, ready to snap. This submergence process is tied to the complex dynamics of magnetic buoyancy and the sun's convective layers. And honestly, we don't fully understand it. But there's observational evidence that it happens. Active regions sometimes disappear and then reappear weeks or months later in the same location or nearby, with renewed strength. The magnetic structure never died. It just went dormant. The mechanism behind magnetic submergence involves the balance between magnetic buoyancy and aerodynamic drag forces in the convection zone. Magnetic flux tubes are buoyant relative to the surrounding plasma when they're sufficiently concentrated, but that buoyancy can be overcome if the field becomes fragmented or if downflows in the convective pattern drag the field downward. Once beneath the photosphere, the magnetic field continues to evolve according to the complex flow patterns in the convection zone. It can be stretched, twisted, and amplified by turbulent motions. In some cases, it can re-emerge later with a completely different surface topology, but carrying the accumulated stress from its subsurface journey. It's not dormancy in the sense of inactivity. It's more like a chrysalis stage, where profound changes occur, hidden from view. The observational evidence for this process comes from studies of active region recurrence. Several well-documented cases exist where sunspot groups emerged at specific longitudes, produced significant activity, decayed, and disappeared, and then re-emerged at the same or nearby longitudes days to weeks later with renewed complexity. The most famous example is from solar cycle 23, when active region 9696 produced major flares in November 2004, decayed to invisibility, and then re-emerged in December as AR 9705. with an even more complex magnetic structure that generated additional X-class events. The statistical likelihood of independent flux emergence at precisely the same longitude is low enough that most researchers accept these as genuine recurrences of the same underlying magnetic system. If that's what happened with AR 4366, then the 18-day window between when it rotated out of view and when it could potentially rotate back into Earth-facing position isn't a grace period. It's an incubation period. The rotation cycle of the Sun means that by around May 20th to May 22nd, 2026, depending on exact latitude and differential rotation rates, anything at that longitude will be facing Earth again. If AR 4366 resurfaces, and if it resurfaces stronger rather than weaker, then we're not just looking at a return of a known threat. We're looking at an escalation. The differential rotation of the Sun complicates the prediction slightly. The Sun doesn't rotate as a solid body. Instead, the equatorial regions complete a rotation in about 25 days, as measured in the Sun's own reference frame, while higher latitudes take progressively longer, up to about 35 days near the poles. Active Region 4366 was located at approximately 15 degrees north latitude, where the rotation period is about 26.5 days. From Earth's perspective, which is also moving in orbit around the Sun, the synodic rotation period, the time for a feature to return to the same apparent position as seen from Earth, is about 27 days. Do the math, and the central meridian passage, when the region would be optimally positioned for Earth-directed eruptions, falls right around May 21st or 22nd. But here's the twist that should keep you up at night. Active Region 4366 might not even be the main concern anymore, because while it was rotating away, something else was detected, and it might be bigger, stranger, or connected in ways we're only beginning to suspect. The Farside event on May 8th wasn't just a signal that activity was continuing out of view. It might have been the emergence of a new player in this unfolding drama, or worse, the revelation that we've been watching individual acts of a much larger performance. The question is whether that Farside eruption represents the same magnetic engine expressing itself in a new location, or whether we're about to face something entirely independent but equally threatening. Either way, the rotation will soon bring it into view, and we'll have our answer whether we're ready for it or not. When scientists detected that major Farside flare event in early May, the immediate question was, how big is it? Size matters in solar physics because larger active regions generally have more magnetic flux, more energy storage capacity, and higher probabilities of producing powerful eruptions. But size is also a misleading metric if you focus on it too narrowly. A massive sunspot group with a simple, orderly magnetic configuration might never produce a significant flare. Meanwhile, a smaller region with a complex, sheared delta structure can explode with terrifying efficiency. It's not just about how much magnetic field you have. It's about how that field is organized, how it's twisted, and how unstable the geometry is. The Farside detection methods I mentioned earlier, heliosismology and indirect radiation signatures, can tell us something is there and that it's active, but they can't give us the detailed magnetic maps we'd get from direct observation. We don't know the exact size of this incoming region. We don't know its magnetic class. We don't know if it's a single coherent structure or multiple smaller regions clustered together. What we do know is that it produced an energetic event significant enough to register on our instruments, despite being on the opposite side of the Sun. That tells us it's not trivial. Now, let's talk about context, because this isn't happening in a vacuum. In mid-January 2026, Earth experienced a G4 geomagnetic storm, a severe event that caused widespread aurora displays, disrupted satellite operations, and stressed power grids at high latitudes. That storm was triggered by a CME from an active region that, at first glance, didn't look particularly threatening. It wasn't the biggest sunspot group on the disk. It wasn't the most magnetically complex, but it was geometrically primed, oriented just right, and it launched a CME with the perfect combination of speed, density, and magnetic field orientation to slam into Earth's magnetosphere and compress it hard. The surprise wasn't that the storm happened. The surprise was that we didn't see it coming with the intensity it delivered. The lesson from January is that surface appearance doesn't tell the whole story. Magnetic geometry, the three-dimensional configuration of field lines and how they're embedded in the solar wind, can matter more than raw size. And here's where we get into uncomfortable speculation. What if the far side region we're detecting now, the one that will rotate into Earth-facing position in the coming days, isn't just large or complex? What if it's part of the same magnetic system that powered active region 4366? What if they share a subsurface route? I'm not saying this is proven. I'm saying it's a hypothesis that fits the observations. The sun's magnetic field is generated deep in the interior by a dynamo process we still don't fully understand, and that field rises to the surface in discrete flux bundles. Sometimes those bundles emerge at multiple points, separated by distance but connected below. If AR 4366 and the incoming far side region are branches of the same underlying structure, then we're not watching separate actors. We're watching one engine with multiple exhaust ports, and that engine has been firing on all cylinders. There's another concept we need to talk about here, and it's the idea of a primed magnetosphere. Earth's magnetosphere is the magnetic bubble that protects us from the solar wind. It's constantly being buffeted by the stream of charged particles flowing from the sun, and it responds dynamically, stretching and compressing like a sail in the wind. When a major geomagnetic storm hits, it doesn't just affect us and then reset to normal. The magnetosphere can remain in an agitated state for days or even weeks, with elevated levels of trapped radiation, stretched magnetic field lines, and reduced shielding efficiency. If another CME arrives while the magnetosphere is still recovering, even a moderate eruption can punch above its weight and trigger effects far stronger than it would under normal conditions. Earth's magnetosphere is still settling from the January G4 event. We had additional moderate storms in February and March. The system hasn't had a long quiet period to fully relax. If a fast, well-aimed CME from this incoming region hits us in the next week, it's walking into a primed environment. The kind of environment where a G2 forecast can turn into a G4 reality because the initial conditions were off by a few percentage points. And that brings us to the question that makes institutional scientists uncomfortable. The question that sounds too much like conspiracy theory or pseudoscience to say out loud in polite academic company. But it's a question that refuses to go away, no matter how many times it's dismissed. There's a thing called the global electric circuit, and before you tune out thinking this is where I veer into fringe territory, let me assure you, this is mainstream atmospheric physics. The global electric circuit, or GEC, is a continuous flow of electric current between the Earth's surface and the ionosphere, driven primarily by thunderstorms. At any given moment, there are roughly 2,000 thunderstorms active somewhere on the planet, and they act like batteries, pumping positive charge into the upper atmosphere and creating a potential difference of a few 100,000 volts between the ground and the ionosphere. That current flows constantly, completing the circuit through fair weather regions where conductivity is higher. It's a real, measurable phenomenon, and it's been studied for over a century. Now, what does the sun have to do with this? Quite a bit, actually. Solar radiation ionizes the upper atmosphere, creating the charged particles that make the ionosphere conductive. Solar wind and geomagnetic activity modulate that conductivity, changing the resistance of the circuit. When a geomagnetic storm hits, the ionosphere gets pumped full of extra energy, and the GEC responds. The mainstream scientific position is that these effects are real but limited, Yes, solar storms influence the ionosphere. Yes, the GEC changes. But the impacts on ground-level phenomena, on weather, on seismic activity, on human behavior are considered indirect, weak, and poorly correlated. That's the official line. And yet, the correlations keep showing up. During major solar flux surges, during periods of elevated geomagnetic activity, there are statistical blips in earthquake frequency, volcanic eruptions, and even atmospheric chemistry. Not strong correlations, not smoking guns, but persistent signals that refuse to go away, no matter how much statistical noise you try to bury them under. Some researchers argue these are coincidences, the inevitable false positives you get when you analyze enough data. Others suggest there might be a real coupling mechanism we don't understand. Something subtle and systemic that links solar activity to Earth's interior processes through electromagnetic induction or stress changes in the crust. I'm not here to tell you that solar flares cause earthquakes. I'm here to tell you that the question isn't as crazy as it sounds, and the fact that institutions avoid it so aggressively should make you curious. Because there's a societal dimension to this as well. Multiple studies have shown correlations between geomagnetic storm activity and human health metrics, increased rates of heart attacks, strokes, psychiatric admissions, and even traffic accidents during periods of elevated geomagnetic disturbance. The proposed mechanisms involve disruption of circadian rhythms, changes in melatonin production, and electromagnetic interference with biological systems. Again, these are correlations, not proof, but they're persistent. They show up in data sets from different countries, different decades, different methodologies. There's a hypothesis, rarely stated outright but implicit in some of the research, that the sun acts as a periodic reset button for coupled Earth systems. Not through direct energy transfer, because the sun's output doesn't vary enough for that, but through subtle modulation of the electromagnetic environment that living and geological systems have adapted to over billions of years. When that environment shifts rapidly, when the ionosphere gets hammered by a G4 storm and the GEC spikes, maybe it's not just satellites and power grids that feel it. Maybe the entire system, biological, atmospheric, geological, twitches. Why do institutions avoid this framing? Partly because it's hard to prove and easy to sensationalize. Partly because it opens the door to pseudoscientific claims and catastrophism. But also, I suspect, because it challenges the idea that we fully understand the systems we're embedded in. It suggests that space weather might not be an external threat we can simply engineer our way around with better shielding and forecasting. It suggests we're part of a coupled system, and the sun's behavior affects us in ways we can't isolate or control. That's an uncomfortable thought for a civilization that prides itself on mastery over nature. If the next major CME from this incoming active region hits Earth in the coming days and triggers a G4 or even G5 storm, watch what else happens. Watch the data. Not just the power grid reports and the satellite failures, but the quieter metrics. The atmospheric electric field measurements, the seismicity logs, the hospital admission rates. And ask yourself whether the patterns you see are just noise or whether we're part of something larger than we've been willing to admit. Here's something that didn't make headlines, but should have. In late April 2026, solar physicists monitoring the solar wind noticed an anomaly. The solar wind is the continuous stream of charged particles flowing from the sun's corona out into interplanetary space. Under normal conditions, its density, speed, and magnetic field strength vary within predictable ranges. During solar minimum, it's slow and sparse. During solar maximum, it's faster and denser, especially during and after CMS. But the long-term trends are well established. We have decades of data. We know what normal looks like. Except in late April, during a period of relatively low flare activity, the solar wind density spiked without a corresponding CME event. It wasn't a massive spike, Nothing that would trigger alerts or concern at NOAA, but it was statistically unusual. Solar wind density elevated by about 20 to 30% above the baseline for that time in the solar cycle, and it stayed elevated for several days before gradually declining. No obvious source, no clear trigger, just a pulse of extra particles flowing past Earth's orbit, like the sun had quietly exhaled a breath we didn't see coming. Why does this matter? Because Earth's magnetosphere responds to solar wind pressure. When the density increases, even without a change in speed or magnetic field orientation, the magnetosphere compresses. The boundary between the solar wind and Earth's magnetic field, called the magnetopause, shifts inward. Satellites in certain orbits experience increased drag. Radiation belt dynamics change. And here's the kicker. The magnetosphere doesn't immediately snap back to its original shape when the pressure drops. There's hysteresis, a lag in the system's response. It takes time to recover, time for the magnetic field lines to relax and the trapped particle populations to redistribute. This delayed recovery time is something scientists model carefully because it affects how we predict the severity of geomagnetic storms. If a CME arrives while the magnetosphere is still compressed from a previous event, the impact is amplified. The models assume a certain recovery timescale based on historical data. But what if that timescale is changing? What if the magnetosphere in 2026 is recovering more slowly than it did in previous solar cycles? There's some evidence, tentative and debated, that this might be the case. Researchers comparing current magnetospheric behavior to similar phases of past solar cycles have noticed subtle differences: longer persistence of disturbed conditions, slower relaxation of radiation belt fluxes. It's not dramatic, and it's within the error bars of measurement uncertainty, but it's there. And if it's real, it means our baseline assumptions might be slightly off. The models that predict a G2 storm could be underestimating by half a category or more if the initial state of the magnetosphere isn't what we think it is. Energy is lingering longer in Earth's system. Whether that's due to changes in the solar wind properties, changes in the magnetosphere itself, or some combination of both, the practical effect is the same. We're more vulnerable than the forecasts suggest. A moderate CME that would normally produce a G2 event might push us into G3 territory. A strong CME aimed for G3 might deliver G4. The margins are tighter than they used to be, and the quiet metrics, the ones that don't make the news, are the canaries in the coal mine singing a slightly off-key song. This isn't alarmism, it's pattern recognition. When systems that have been stable for decades start showing subtle deviations, it's worth paying attention. Because subtle deviations are often the precursors to phase transitions, the early warning signs that something fundamental is shifting. And it's not just the sun behaving strangely. The wider cosmic and technological context of 2026 is turning out to be more uncomfortable than anyone predicted. Let me tell you about a failure that happened in March 2026, and it had nothing to do with solar flares. It was an artificial intelligence system designed to predict space weather, one of the new machine learning models that were supposed to revolutionize forecasting by finding patterns in the data that human analysts might miss. The AI had been trained on decades of solar observations, magnetospheric measurements, and geomagnetic storm outcomes. It was good, really good, accurately predicting storm intensity 70 to 80% of the time, until it wasn't. In mid-March, a moderate CME was launched from an active region near the sun's equator. The traditional physics-based models predicted a G1 storm, maybe G2, if the magnetic field orientation was favorable. The AI model agreed, spitting out a G1 forecast with high confidence. What actually happened was a G3 storm that knocked out several aging satellites and caused voltage irregularities in power grids across Scandinavia. The AI didn't just miss by a little, it missed by 2 full categories, and when researchers dug into the diagnostics to figure out why, they found something unsettling. The model had encountered an edge case, a combination of solar, wind parameters, and magnetospheric conditions that fell just outside the envelope of its training data. It wasn't that the physics was wrong. It was that the AI had never seen this exact configuration before, so it defaulted to the nearest match in its learned patterns, and that match turned out to be profoundly misleading. The lesson isn't that AI is bad at forecasting. The lesson is that AI, like all models, is only as good as the regime it was trained on. When the system you're modeling starts to behave in ways it hasn't behaved in the past, all bets are off. And here's the uncomfortable truth. Multiple complex systems are showing nonlinear behavior in 2026, and it's not just space weather. The James Webb Space Telescope, which has been revolutionizing our understanding of the early universe and exoplanet atmospheres, recently returned data from a protoplanetary disk around a young star that doesn't fit our formation models. The disk's structure, the distribution of dust and gas, the gaps and rings, all of it is more complex and chaotic than simulations predicted. It's not proof that our models are fundamentally wrong, but it's a reminder that the universe doesn't care about our equations. Closer to home, Earth's radiation belts, the donut-shaped zones of trapped charged particles surrounding our planet, have been behaving erratically. Particle fluxes that should decay predictably after a storm have instead shown unexpected spikes weeks later, as if energy is being recycled through the system in ways we don't account for. Some researchers suspect this is related to electromagnetic wave interactions, chorus and hiss waves in the magnetosphere resonating with particles and accelerating them to high energies. But the timing and magnitude don't match theoretical predictions, and we're stuck in the uncomfortable position of watching it happen without fully understanding why. When multiple systems, solar, magnetospheric, technological, cosmic, start misbehaving at once, the temptation is to look for a single unifying cause. Maybe there's something about this phase of the solar cycle that's different. Maybe the interplanetary medium has changed in subtle ways we haven't measured. Maybe our instruments have degraded and we're seeing artifacts instead of reality. Or maybe, and this is the possibility I want you to sit with, the systems themselves are fine. It's our models, our assumptions about how stable and predictable these systems are, that are breaking down. We've spent the last 50 years refining our understanding of space weather, building better instruments, collecting more data, training smarter algorithms, and all of that progress is real and valuable. But it's been built on the implicit assumption that the sun, the magnetosphere, the radiation belts, all of these systems oscillate within known bounds. That they're variable, yes, but predictably variable. What happens when they're not? What happens when the baseline itself shifts? When the old rules stop applying and the new rules haven't been written yet? The sun doesn't owe us stability. The magnetosphere doesn't owe us predictability. And the universe at large certainly doesn't care whether our models can keep up. We're living in a time when the confidence we've placed in those models, the sense of safety we derive from forecasts and probabilities, is being quietly tested. Not by a single catastrophic failure, but by a creeping accumulation of surprises, anomalies, edge cases that shouldn't be happening, but are. So let me bring this back to the question we started with. Is the next G4 storm coming? Maybe. The far side active region is rotating into view. Active region 4366 might resurface stronger than before. The magnetosphere is primed, the solar wind is behaving strangely, and the margins of error in our forecasts are tighter than we'd like to admit. A G4 storm is absolutely possible in the next 7 to 14 days. But here's what keeps me up at night. And it's not the G4 scenario. It's the possibility that we're asking the wrong question. What if the danger isn't a single storm we can track and prepare for? What if it's the slow realization that the systems we rely on, the technological infrastructure, the forecasting models, the geophysical stability we take for granted, are all coupled in ways we don't fully appreciate? What if the sun is part of a larger feedback loop that includes Earth's magnetic field, the ionosphere, the global electric circuit, and maybe even biological and geological processes we've dismissed as unrelated? When you start connecting those dots, the picture that emerges isn't one of isolated threats that we can engineer our way around. It's a picture of systemic vulnerability, where the next big event isn't necessarily the strongest flare or the fastest CME, but the one that hits us at exactly the wrong moment, in exactly the wrong configuration, and reveals just how fragile our assumptions really are. We've built a civilization on the assumption that the environment is stable, that the sun is a steady beacon, that the ground beneath our feet and the sky above our heads will behave within predictable ranges. For most of history, that assumption has held, but we're entering a phase where it might not, where the combination of solar maximum, technological dependence, and subtle shifts in coupled systems could produce outcomes we don't have categories for. And when multiple complex systems misbehave at once, the danger isn't any single event. It's our confidence in the models we use to feel safe. The X8.1 flare was not the event. It was the signal. The question now is whether we're paying attention to what it's signaling, or whether we're too busy staring at the forecasts, trusting the models, and assuming the next storm will look like the last one. Because if there's one thing 2026 is teaching us, it's that assumptions are comfortable right up until the moment they're not. And that moment might be closer than we think.